How is it going? Let me, I'm a little not quite prepared enough. Let me pull up the chat. All right. Got a couple of people in the chat already. Let's roll. How, well, let me make sure that we got everything shared that we need to have shared. Slides, doesn't work. As usual. Let's figure out what's going on. OBS, man. OBS. Okay, slides work. This works. That works. Perfect. Okay. Hey, David Xterra made it to Toddler 111. Made it to or made it through. Either way is a great accomplishment. Let's check how people are doing on the scoreboard. So many blue belts. Awesome. Nice. Toddler 2 level 10. Oh, that's great. So you got through the first Yan 85 level. Figured out mmap. Awesome. All right. 13 hours to figure out mmap. That's fair. So just to make you feel maybe a little better, when I wrote the me and my teammates wrote the Hyper-O challenge for DEF CON. This one. No, it's the whole thing. Dash. Yeah, this guy. Man, when we wrote this challenge in Hyper-O, there's in the main module. This is basically a mini hypervisor. And you mapped in code and data into the virtual machine using mmap. So we had an mmap handler. This alone took me easily 48 hours cumulative suffering time. Just this fucking handler. It was insane. It was insane. Pretty bad news. And the one of the massive time sinks was that in my test case I was opening the file without write permissions. I was opening read only, and so then when you try to mmap on that file descriptor for a writable page, no good. All right. So, what questions does everyone have? I figure I'll just go through whatever questions people have and go from there. Ideally on older modules, if anyone has questions on older modules, because that I think is probably the best bang for the buck of getting people's grades up. Of course, Toddler 2 if you have them as well. I forgot to announce that we are live. Awesome. Otherwise, we'll just sit here. I can go make tea. I didn't have time to make tea. Can I talk about Baby Kern 12? I can talk about Baby Kern 12. Let's take a look at Baby Kernel 12. Let's log in. Let's launch Baby Kernel 12. Oh, Baby Kernel 12. That's the final boss. All right. Start it up, and then I'll try to remember things about it without looking at my notes. All right. Baby kernel 12 is launched. Specifically how to get the assembly for it. Do you mean how to reverse engineer, how to start reverse engineering the module? Here, let's copy it in. Okay. I see. How to search for things in visitors. All right, let's start from basics and disassemble this guy. So first of all, let me SSH in. Awesome. All right, we have sorry, the baby was making noise. I was trying to listen what was going on. Okay, we have the following. So it's a kernel module. The typical problem of not SSHing in. It's like that is way too many. Hackerdojo.pwn.college. Okay. So we're connecting up. It's booting up. Got some logs going. It's booting. In about 2 weeks, this infrastructure is going to boot super fast. It's going to be really cool. We're moving it to a machine that has nested virtualization. All right, so we are in the VM. We have the challenge loaded. And of course, it's a module. It talks, let's just guess that it talks over pwn.college. So in this one, pwn.college is not world readable, but luckily we have this user space binary that is set UID. So we can launch this, hit the user binary, and presumably use that to talk to the kernel. If we actually open this user binary in, let me find this guy. Okay, if we open the user space binary in IDA, right here. Awesome. And if we reverse engineer, we'll see it's pretty simple. Actually, it'll talk to us if we launch it, so let's just launch it. All right, we launch it. So, okay, you may upload custom shellcode to do whatever you want. The challenge will only allow certain system calls. Attempting to load the flag into memory. And the flag has been deleted. And it opens the file descriptor for us. And what's it called? Maps in shellcode and reads. All right, so in level 11 of this module, we of baby kernel, we had to go and dig through memory for the flag that was being held by this process. But oops, I didn't switch over here. But in this level, things are a bit trickier, right? So let's see. We load the flag. What does this do? This will read the flag. Awesome. Then we unlink the flag. And then we read some shellcode. We initialize basically shellcode so that we only have the system call write available. And then we execute the shellcode. Wait, is this level 12 or not? Re-unlink the flag. Ah, okay. We fork off a child to read the flag, and the child reads the flag. And so the process that reads our flag is dead. There's no more process that read our flag. So let's download level 11 real quick so I can show you that difference there. Right? So let me SCP it over. Load up level 11. All right. Looks very similar, right? Upload extra system calls. Challenge will allow only certain calls. It loads the flag, unlinks the flag, opens up pwn.college, maps in some shellcode, reads in shellcode, only allows write, and executes our shellcode. Exactly the same, except for load flag is different, right? Here, how do I do this? Okay, here. Here, in level 11, in load flag, it sleeps forever. The child process that reads our flag. In level 12, load flag, the process exits. This is level 12, exits, level 11, reads forever. How do we... I don't have any of my keyboard shortcuts because they, of course, don't work in this sudo x session. So we're going to do this. All right, level 12 on the left, level 11 on the right. Level 11 will chill out and sleep. Level 12 will exit immediately, right? Of course, if you chill out and sleep here, there's question on stream. Are we cracking CTF problem? We are cracking a problem talking about how to conceptually approach level 11 and 12 of the kernel module of pwn.college. pwn.college is a early stage education system for cybersecurity. It gets you through basic concepts in binary analysis and exploitation. All right, back to work. So, how would you exploit level 11? Right, you'd exploit level 11 by running shellcode in the kernel, which the challenge allows you to do. In that shellcode, disabling seccomp, which you have done in earlier levels, becoming root, and being able to do anything from there. Because this process still exists, you can exec GDB, which can attach to this process and recover the flag, right? Super simple. Especially because it's looping here. You know where this guy lives. It lives in the BSS at a fixed offset. Everything is easy. In level 12, the flag also lives in the BSS, also at a fixed offset. At a place where you know where it is, at an offset of hex 100 into a page. But, wow, IDA does not do well with this tiny screen. But, let me resize this, there we go. But the process is gone. The process exits as soon as the flag is loaded. So there's, even if you make this guy root, or it is root, if you disable seccomp, you are you're still screwed because there's no flag, no process to attach to that has the flag, and the flag itself is gone because immediately after this, and before running your shellcode, god damn it, where is it there? The flag is unlinked. So what do you do? All right, if you recall the lecture on virtual memory, this lecture right. Uh-oh, Connor, we don't have this lecture page updated. Anyways, if you go to this lecture page, if you recall, yes, this lecture, the memory management lecture, there's a lot of discussion about physical memory versus virtual memory, and basically the difference between the two. When a process is created, it gets virtual memory mapped into its process space, or the kernel takes physical memory and assigns it to the process, into the process virtual memory space. When the process calls mmap, it gets more memory assigned. When it calls munmap, it releases it. When it dies, when it terminates, that process releases all of its virtual memory. Some of that virtual memory had this flag loaded. There's a virtual page of memory that was mapped into location 404000 in this process's address space that has the flag in it, and the process terminates and gives it back to the kernel. But the kernel doesn't just throw it in the trash. The kernel takes that memory and leaves it in some sort of a list of free space that it can give to process later. And because it's expensive to override that memory with zeros, that's like a lot of memory operations, it'll wait to do that until it has to. It'll wait to do that until that memory is actually returned to some process. And in the meantime, since you have shellcode execution in the kernel, you can try to get at that memory. Now, the next question is, well, how do we do that? And the easiest way to do it, of course, you have to write shellcode to do it, but the easiest way to write that shellcode is actually what we're going to try right now. This is a YOLO idea. We're going to write it in C. We're going to write a kernel module that's going to go through all memory in the kernel and find the pwn.college, the flag, dump it out with print k, and we're going to see what that assembly looks like. And that's the assembly that you can convert to assembly to pass into the challenge. Obviously, our solution with the kernel module will only work in debug mode. So let's do it. This is level 11, so let's not do level 11. We can, of course, use the same solution for level 11 somewhere in physical memory. It'll have it, but let's launch level 12. Where the fuck is it? There? Yeah, there we go. All right, I'm gonna launch level 12. Awesome, we're in level 12 now. We have some hello module, right? Yeah, this is a very, very simple hello module. So here's what we're gonna do. We're going to, what's the smallest module I created? Yo? No, Yo is really big. Okay, but this module does nothing. All right, so we'll do hello, and then we'll do flag search. It will be our module. And then when this module gets loaded, it's just going to do the search. It's going to print k it, and then that's it. All right, so what are the how do we get at physical memory in the kernel? That's the first question, right? So our goal is to search through all memory on the system, looking for the flag, assuming that when the process that loaded the flag died, it didn't release the memory. Sorry, it released the memory, but that memory didn't yet get overwritten. How do we do this? We're going to I'm just thinking if this is the best way to do it. Well, it's not the, well, okay, let's just see. We'll write the base case. If it doesn't work, we'll expand. If we look at the slides again for the kernel, we go to memory management and we say, how do we get at memory in the kernel? There's two functions, two macros in the kernel that are useful. One is phys to virt. We give it a physical address. It gives us a virtual address. That's what we're going to use. We are going to say and what do we, sorry to keep bouncing around all over the place. We know, by the way, that the flag is loaded hex 100 of the way into a page, right? Because this is its address in memory. And the page is always aligned to hex 1000. So it would have been mapped into 404.000. And at 404.100, it's going to be pwn_college curly. All right. So let's do this. And say we're gonna go through a bunch of memory at starting from hex 100 to, this is physical memory. How much RAM is in this machine? Let's see. But it'll be something 100. However much maximum RAM there is, physical RAM. And at every time, we're going to increment it by 1 page. And we're going to see if, actually, let's just match for the first 8 letters of pwn.college, so we don't have any weird. So first, we say, we get the virtual address of this page that is mapped in the kernel. In the kernel, there's a very convenient mapping of the entire physical memory into the kernel's virtual memory. We use phys to virt I. Awesome. And then if mapped adder, let's use pwn pack for get pwn tools out here. Pwn, there's no pwn pack. God damn it. Pwn hex, and then we'll reverse it manually. Wait, do we reverse it manually? Yes, we do reverse it manually. All right, this is pwn_call. No. That actually sorts it. We want rev. There we go. No, that we want tac. There we go. Perfect. All right, so now we have a little endian pwn call. Okay. Okay. Wait, pwn underscore. Am I? Since we're in practice mode, we can confirm. Oh, pwn.college. Wait, it's pwn.college? has been pwn.college this whole time and I just haven't noticed it. Okay, well, instead of 5F, it's 2E. Where's my 5F? 2E, okay. Last year it was underscore, and I just been, wow, cool, okay. Awesome, so if it's pwn.call, then what we're going to do is print K, current info, flag, %s, mapped adder. Boom. The end. This should be enough as long as we figure out how much RAM we have. We can figure that out with this. So we have this much RAM. Let's grab an IPython, take that, convert it to hex. Okay, that's a weird number, but that's okay. We just round this. Let's round it down. We'll assume it's just weird. Okay, so we'll assume we have this much RAM, so all of this should work, and hopefully this will be good to go. Let's actually do this on unload time. That I think will be better, because this will get loaded by the infrastructure when the thing boots. Looking for flag, and goodbye. And here we should say flag was at LX, and this should stay long, and in fact it should be unsigned long. And here we say mapped adder. All right, let's see this incredible infrastructure. Wow, it actually, okay, there's a complaint with the format. It expected a type char. Let's fix all of the warnings just to make sure that everything is legit. Type long unsigned int. I gave it a long unsigned int. I gave it a pointer. So how about %p? Well, whatever, it's fine. We have root, we can check. Okay, so for bids, we need to declare this up ahead. Boom. All right. Now we have our module in /challenge. If we do a VM restart, while that is booting up, let's disassemble this. Here is our shellcode fundamentally, right? And you can see that what is this called? Is this, let's add some nops before and after hour, just as a oh yeah, I forgot dash r. Okay, so our shellcode is surrounded by these nops, so that, or not our shellcode, our flag search code, so that we can see it a little easier. Let's do VM build. All right. Dump. Okay. There we go. So this is the print K. Okay, yeah, of course, because we logged the flag out. So this is the print K to log the flag out. And you would have to, as you can see, this has no, there's a couple of relocations that you would have to manually make when you extract the shellcode by looking them up in the KAll sims. One is where print K is. The other one is some other addresses, but of course we can eliminate that by crafting the shellcode more carefully. But basically, it's right here is our code that searches through the physical memory and dumps it out. So let's give it a try. So we have debug loaded. All right, we run /challenge. Okay, boom. Let's see, we rmod debug. No, okay, well, we're cheating because we have root. Okay, we rmod debug. Do dmessage. It did not find the flag. So there's a couple of possibilities for why it didn't find the flag. One possibility is that my search is wrong, which is very possible, right? So let's see. We start with an OX100. This might be very wrong. Would this be wrong? _PWN dot COLL. Should be good. So then the other possibility is that because we ran a command afterwards, it acquired this memory, and then we got fucked. So let's. Oh, what just happened here? My X screen with IDA went into screensaver mode. All right, let's restart the VM. Try that again, because the memory reallocation doesn't always happen super stably. And then we'll try to figure out other possibilities. One thing that we can do is actually make this a true scanner. So not only it'll scan page by page and then byte by byte to find pwn.college. Okay, so we can do that. But first we can do, I mean, obviously this you can't do not in practice mode, but we're just doing a proof of concept here. So we run the challenge. Okay. And now we remove the debug. Oh, no flag still. Okay. Let's just see if there's any. And then, of course, next, soon we'll dive into GDB to figure out what is going on. But first, try it in the previous level as a sanity check. That's a great idea. That's a brilliant idea. Let's do that. We'll try it in, we'll try it in level 11, because it's the same thing. Just level 11 keeps the flag for sure in physical memory because the process is still alive. So we're going to VM connect here. Well, let's first do VM build flag search. VM connect. And we'll do VM connect here as well. Okay. Okay, the flag is now in memory. And if we remove the debug module, dmessage, no. Okay, so our flag code, our module is wrong. Let's SSH in here. All right. A couple possibilities. One is that on level 11, maybe it's not at hex 100 of an offset. Let's take a look. Load flag to here. It's at hex 120 on level 11. So let's adjust that. Actually, let's just write it so that it scans every byte of every of everything. So we're going to go tick up in pages. For every page, I'm going to go through every byte. And actually, let's, God damn it. Okay. We go through every byte and not the last 8 bytes. Let's not deal with what happens if the next page is unmapped. It's if you're at the last physical map page of the kernel, it's just going to be a nightmare. And then we go through and we make sure and we check for that flag and we print it out if so. This might take longer. It will take longer. It'll take 1,000 times, hex 1,000 times longer, but hopefully it'll still be fast enough. All right, let's build it. J is undeclared. That's fine. Okay, let's build it. Amazing. Now the mod probe, insmod challenge debug, reload it, sudo. Okay. No. Okay. Next, the next suspicion. Let's see. Let's make sure it took some time. Okay. Scanning through all of memory. Ah. Okay. The next problem. No one caught it. No one caught it. Check this out. This is how much memory we have. I converted it to hex. This is in kilobytes. And probably this is actually in 10 to the 24th. That's why I didn't convert to hex cleanly. Python here is going to be slow. Oh my god. All right, this, is it in kilobytes? No, it's in kilobytes. That is how much memory we have. That was how many kilobytes of memory we have. All right, so we were only searching for the first 0.1% of memory. Now, let's undo this because that's going to be a massive nightmare to search every byte. We'll just search at the correct offset, 120 in level 11. And we go through incrementing until we reach the last page. And let's see what happens. I also failed to add J to I over here, so that wouldn't have worked anyways. But again, we're not searching every byte anymore. We're just searching the correct offsets. Let's compile it. And let's insert it. Okay, rmmod. Okay. Haha! Okay, level 11 solved. Now let's solve level 12. Now, of course, we solved level 11 with the approach of level 12, which wasn't intended. So let's boot up level 12. Boom. All right, while this boots, let's change the offset. Change the offset to hex 100. Okay. We build it. Then we'll talk about how to convert this into shellcode. All right. Here we go. Let's just, okay. Boom. All right, the flag is gone, and it has been loaded, and the process is dead. And now vrmod. What? Okay, this might, okay. Yes, it got deleted, damn it. All right, let's restart the VM. Yeah, solving 11 the intended way is much more interesting than the unintended way. And it's much more realistic, too. Rather, it's probably more applicable real world. That there will be another process you want to mess with once you're root, rather than digging through unmapped memory. Map a ton of memory in the child. Yeah, we could map a ton of memory and spray the flag all over the place. But I think this is a problem specifically because of the way that I'm testing it. Okay, so I have my debug module, rmmod debug, boom. Okay, we launch it, rmmod debug, dmessage. Hex 100, pwn.college. I did insert the module first. It's just the rmmod that's a problem. What's the easiest way to do this? Python. Okay, I know how to do it. Isn't there an rmmod remove module? Kernel syscall remove module. Delete module. Okay. No. OS doesn't have a... No, that's obviously... Delete module system call. Come on, how do we... fuck it, we'll just write a quick program. This is going overkill to use the stupid thing that we were... our workaround. Okay. We're going to write a quick program that'll just use the actual system call. And then remove it. Delete module, flags. What is flags? Okay, we'll just do flags 0 and hope for the best. Whatever, it'll work. Okay. So, connect up. Flag is the... God damn it. Connect up as soon as that boots up. All right. So we run this. But before we do, we actually have this guy running. Okay, boom. Now when so the flag has been loaded, the process died. Now our mod happened. And it didn't remove the fucking module. I did restart the challenge. Name is the name wrong? It's still loaded. Oh, I wasn't root. God damn it. Okay. Let's try to. No. VM restart. Okay. VM connect. VM connect. Oh, restarting the whole challenge because the flag is deleted. Oh. Good call. So, possibly what happened was that... So, Connor, we should... I see what happened. So when I restarted it, the flag was already deleted and the challenge doesn't check if the flag has already been deleted, right? We should make the challenge check. Let's make an issue on that. No, it doesn't complain. We should make it complain loudly. Yeah, it should yell if the flag is already gone, because that... If it wasted 30 minutes for me, it can probably waste a depressing amount of time. Okay, so again, we're going to do something very simple. We're just going to go back to basics and try to run the challenge. It'll delete the flag, but load it into memory. And then we're just going to remove our debug module, which on remove will search through all of memory and give us the flag. So, and I don't think that physical memory will be recycled in time for this to be a problem, but if it is, we'll restart it. Okay, here we go. Boom. Fuck. We forgot to pop this in there. Okay, we're just gonna get really player luck if we ints mod debug and then rm mod debug. Okay, the flag was gone. So we restarted the thing. Or we could recreate the flag, you're right. All right, VM connect. No, we want VM build flag search.c. That probably wasn't, that probably happened in time there. All right. So, let's load our module again, debug mode, perk. Run this guy. Then we will be ready to, oh, okay. Flag is in memory, physical memory, and we still didn't find it. So now we restart the challenge. We restart the VM. We're gonna quadruple check that this offset is correct. Hex 100. This freaking flag in level 12 is at offset hex 100. Gonna connect to the VM, and then we'll use our sleep unload to unload the module. Because this for sure can work. But worst case, we'll just extract that shellcode and then run it in the kernel. All right. Connor, we should also randomize the offset to that flag in the BSS. Let's add a issue for that. Okay. Boom, boom. Here we go. RMod. Yep, delete module turn 0. Yes! We caught it. Why the fuck is it at... What is that? That address doesn't make any sense. This address makes absolutely no sense, does it? It should end in hex 100. Well, why could it? Yeah, let's read this. Okay, so let's connect up in GDB, VM debug, and let's read it. Yeah, that makes sense. Oh, well, this is a... Can we call... We can't call fizz2word, but we can figure out... God damn it, come on. No, this is mapped address. This should be a virtual address. Yeah, this is the virtual address. That should be a kernel address. I'm going to go ahead and say that %p is a lie. Let's do this again with LLX. This isn't important. I just want to get to the bottom of this. VM build. Let's restart the chow actually first. Okay, now VM build. VM connect. VM connect. What am I doing? All right, here we're going to run this sleep RMod, and then we'll run the challenge, and LLX is going to tell us the truth. Boom, do message. Okay, %p is a lie, I guess. Why is %p a lie? So this address makes sense. It's a kernel address that looks like part of some user space. I mean, it's a kernel base to which a physical address is added. It's the kernel base at which all the physical memory is mapped, and then offset into that. That base is probably this FFF880. And in fact, if we obj dump this module, we can see that it actually is that. So this is our comparison. Where is the comp? Here's our comparison. And here's the page offset base. So that's a relocation that's resolved when we actually load this module into the kernel. There's a it's put into RSI, and then so if you want to resolve what this actually looks like in kernel memory, then we can connect with GDB and actually, sorry, continue. Let's insmod our debug module. Boom. Okay. Get all the symbols. Our debug module is right here. So if we, okay, and disassemble this function. Hmm, 100 is obviously too many. So here's the knob to begin our shellcode. Here's the knob to end our shellcode. Here is our pwn.college. Here is the initial value of I, and this is our here's where I gets incremented. So between here is the check. This is interesting. So the page offset base is stored in the kernel somewhere. Interesting. So this memory location stores the base of this memory location, rather. It's a rip relative thing, but here we got it. Yep, so that's the base at which virtual memory is mapped into the kernel. Without KSLR, it's always the same. So in your shellcode, you can just add your physical memory address to this, and that becomes a kernel valid virtual memory address. Or you can copy this code, just changing this from a rip relative address, because you don't necessarily shouldn't rely on where your shellcode runs, to this absolute address. The other thing you'll need to change in your shellcode is this call. Call is a relative. This is a relative call, of course, but you can change it to an absolute call by loading this address into REX and jumping to REX. And that is shellcode to solve level 12. And we barely had to write any assembly for it. All right. Awesome. Oh, pointers printed without a specific extension are hashed to prevent leaking information about the kernel memory layout. What the fuck? So that makes sense. So that's why %p didn't work there. Cool. That is level 12, the approach to solve it. Of course, that final step of converting this fully loaded code that we have, where did it go? Right here, into assembly. That's on you. But this is pretty short shellcode. Nice and simple. All right. Awesome. Okay, well, that took longer than expected, and unfortunately I have to run. But I think Connor's planning to hold an office hours tomorrow, and then I will do another office hours on Thursday just to make sure everyone has enough assistance. Crazy. As you can see, it's very easy to get down a rabbit hole Especially when the flag is gone. Cool. All right. Good luck. What's the last day for accepting memes? I think this will be the last week for memes. So the last day will probably be... Connor, how automated is it? Is it a pain in the ass? Connor's thinking. We'll accept memes until grades are due. There you go. Boom. So it's going to be at 12:12, 11:59, 59:59 p.m. Awesome. All right, good luck. Keep on hacking. Use the help channels, and we'll have, I guess, office hours almost every day for the rest of the week. Good luck. Goodbye, hackers, again.